Good morning, everybody.
Morning.
Let me see if this works. I'm trying to use two phones. See if that works any better. Can you hear me?
Mm-hmm.
Okay.
Yeah.
So what I want to do today is show you something on my stove, and it works better if I use this phone to do that. So let me see if I can get this set up so you can all see that. Okay, I think I found it. Let me go ahead and mute this one. Oh gosh. Sorry about that. I hope your ears are okay. Well, this might not work. Let's see though. I'll just keep it on mute and see if that fixes the problem. Okay, so over here, I have two beakers of water. Can you still hear me? Yeah. Hopefully, you'll hear me well enough. So I have one that is just mildly boiling, one that's boiling a lot. And I wanted to show you the temperatures of both of those. So let those sit back on there for a little bit. And in the meantime, right here, doesn't a thermometer show up? I don't know if you can see it or not. But do you see that it's right around 0 degrees Celsius?
Yeah.
So ice water is going to be at 0 degrees Celsius, 32 degrees Fahrenheit, no matter what temperature the ice starts at. I'm going to show that to you. My freezer right here, this is about 0 degrees Fahrenheit, and this is about 0 degrees Celsius. I have another thermometer. We'll use this one in here. Okay, so this one right here, we'll just sit for a few minutes. But you can see right here, it's showing the thermometer or the temperature of the fridge because it was about 34 degrees Fahrenheit. And you can see in here, it's dropping really fast because it's about 0 degrees Fahrenheit in the freezer. So the ice itself would also be about 0 degrees Fahrenheit. So ice can be very cold. But if you put ice in water, like I did over here, then the heat from the water goes into the ice and it warms the ice up, but it won't get above 0 degrees Celsius until all the ice melts. So as long as you have ice and water at equilibrium where you're mixing it around, it will always be at 32 degrees Fahrenheit or 0 degrees Celsius until all the ice is melted. And you can put the ice on a stove. You can do that. And as long as you were to mix it up thoroughly, it would stay at 0 degrees Celsius until all the ice melted. Because all the heat going into, from the stove into the beaker would be going into melting the ice and not warming the water up. Now, once all the ice was melted, then you would start to see a temperature rise, but not until then. Now on here, sorry, I only have two hands. Let me put this down for 1 second. See, because I can't have the thermometer touching the beaker. And that one went down and touched the beaker. So I have this set up where the thermometers are above the beaker. They're not touching the sides of the beaker or at the bottom, because the glass itself would be much hotter than 212 degrees Fahrenheit or 100 degrees Celsius. But as long as they're suspended around the water itself will only be at 100 degrees Celsius. Once it starts to boil, so you can see right here, well, maybe you can see, I'm not sure, but it's about 95 degrees Celsius. It's not yet boiling. Same thing for this one, it's at 97 degrees Celsius. So give it a few minutes to boil. We'll come back to that. Hopefully y'all can see that okay. That didn't work as well as I was gonna work, but you can see on here, actually I just turned that video off, but it's now at about 11, 12 degrees Fahrenheit. So the ice is quite cold. Go ahead and okay, so I think I'll go ahead and add the whiteboard for right now. And we'll take a few notes while the water's heating up. Okay, there's not too many things to go over, but one thing I want to go over is what we talked about last week, where it's this equation. Q equals negative M times heat of fusion. So last week we didn't have a negative sign right here, but what you can think of is this. So this would be when you have ice melting, right? It's going from ice to liquid. So the ice absorbs the heat of fusion when it melts. So when ice melts, what happens is that the heat goes from the ice, or the heat goes from the atmosphere into the ice. So the ice absorbs the heat of fusion. And that's what makes the ice melt. So in order for ice to go to water, it has to absorb the heat of fusion. So ice can be at 32 degrees Fahrenheit, and it will stay as ice until it absorbs the heat of fusion. And it will not change temperature until it absorbs that heat of fusion and then converts over to water, also at 32 degrees Fahrenheit. And then it will start to rise in temperature at that point. So what we could say right here is that the ice had a positive Q. It gained this energy right here. Now, if the reverse happens where you have water and the water turns into ice, as the water does that, it releases heat of fusion. So it would release heat of fusion to go from water to solid. And that's where the negative Q comes in. So we would say negative Q for the water, because the water lost that Q, that lost that heat went into the surroundings. So as water turns into ice, it warms up the surroundings. You actually have heat coming off the water as it turns into ice. And that's why you can have water at 32 degrees Fahrenheit or ice at 32 degrees Fahrenheit. It's a transition temperature where you can have either or. It depends on the heat of fusion. And if the water at 32 degrees Fahrenheit hasn't absorbed the heat of fusion yet, it will stay at 32 degrees Fahrenheit as water. If it releases the heat of fusion, then it will go from liquid to solid. So if it loses that energy, it will turn into solid, and vice versa. Ice at 32 degrees Fahrenheit has to gain that energy, that heat of fusion. And when it does, then it will go from ice to liquid. So going from water to ice, it releases heat of fusion. Going from water to ice, or going from ice to water, it absorbs heat of fusion. Does that make sense? Okay.
Yes.
Let's see. I think it's almost right. Let me go back and see if I can show you those beakers of water. Let me erase this while it's doing that. I exited out of my meeting, so I have to go sign back in first. Okay. Can you see my video on this phone or not? Oh, it's on the other way. Well, that's embarrassing. See, I'm not used to using this phone as for a Zoom meeting, so I forget how to change. I think I just found it. I should have practiced before I did this for you all. Okay, can you see now the thermometer? I know it's
Yeah.
very clear. Oh, so that's well above 100 for there and above there. Okay, so what happened here is the steam heated these thermometers up. I should have let those in here. So steam can get well above 100 degrees Celsius. And that's why steam can cause worse burns than water can. So if they were left in like I did, they're gonna get well above 100 degrees. But if you just get the temperature of the water, let's go ahead and do that again. It should be right at 100 degrees. Now in here, one of them is boiling fast and the other one. I wanted to show you one boiling really fast and one boiling slowly. I have to come back to this one because they're still too hot. The thermometers are still too hot. I'll leave this in there for a little bit. But the point of that was to show you that whether it's boiling fast or slow, the temperature is only going to be 100 degrees Celsius. So it doesn't matter how long they boil for, or whether it's boiling quickly or slowly. The boiling point of water is 100 degrees Celsius, and it will always be at that temperature, and never above that until it all turns into vapor. Now, vapor, though, can be above 100 degrees Celsius. It can be any temperature above that. So the vapor, the steam, can be well above 100 degrees. But the water itself, as long as you have water in the beaker, it will never be above 100 degrees Celsius in the water. It's not possible for it to be. Now, if you were to add things like salt, salt can raise the boiling point of water. And so you could have water about 105 degrees Celsius, maybe 110 degrees Celsius, if you add things like salt to it. But if it's just pure water, it can't get above 100 degrees Celsius. And same thing for ice. Turning into water. If you have ice water, it'll never be below 32 degrees Fahrenheit or 0 degrees Celsius. Now, if you were to add salt to the water, though, it can get quite cold. And you can get some salt and ice mixtures to get below 0 degrees Fahrenheit. But if it's just pure water and ice, it will only be at 32 degrees Fahrenheit or 0 degrees Celsius. Okay, so last week we looked at this equation. We never talked about what this equation means. It's the first law of thermodynamics. In equation form is delta U equals Q minus W. So that's the equation form of it, but what it says is that energy cannot be created or destroyed. It can only change form.
Wait, Miss Holly, I'm not able to see the whiteboard. I don't know if the screen thing is.
Oh, sorry. Let me try this again. I'm glad you mentioned that. Can you see it now?
I still can't. I don't know. Can anyone else see it? It might just be not.
I can see it. I think because I was trying to pin Miss Holly when she was doing the experiment. So if you try to unpin that video, I don't know.
Oh, that's a good idea.
Yeah, but it's not even in one of the options for some reason. It's normally farther down, but I don't see it.
Or maybe just try exiting the meeting and coming back.
Yeah.
That might be easier.
Okay.
Yeah, sorry. I've used Zoom for several weeks now. I still don't really know how to use it properly, but it's a learning experience. Okay, so the first law says this in words, that it cannot be created or destroyed. You can transfer energy between things, but you can't ever destroy or create energy. Okay, and based on that, temperature is a measure of the energy of the molecules. And so the temperature is measuring how fast molecules move. And so there is definitely a limit to temperature, both the lowest and highest limit. 0 Kelvin would be no energy in the molecules. And then there must also be a high limit for temperature, because there must be energy is not infinite. There is amount of energy in the universe that was given to it on the first day of creation. And it can't be created or destroyed. And so whatever energy was given to it on the first day of creation is constant from that day onward. And so there must be a finite amount of energy, which means there must be an upper limit to temperature. Now, we're not really sure what that is exactly. There's a few ideas about that. What we do know is that if you smash 2 lead atoms together, they get to be about 9.9 trillion degrees. And that's the highest temperature that we've ever observed here on Earth or really anywhere. So that's the highest observed temperature. Now, there are higher temperatures that we think could exist, but we haven't observed them. Now, for one of the stars, 200 million degrees is the highest temperature measured inside a star. The sun's about 27 million degrees inside. So it's not nearly as hot as the hottest star. But that's the hottest temperature in the universe that exists out there. 9.9 trillion is the highest temperature that we've ever made here on Earth. Now, as far as the highest possible temperature, there's a lot of debate about that, but they have a few ideas about it. One of them they think is this, that it's 10 to the 27th power Kelvin. So that's 1 with 27 zeros after it Kelvin. And they think that maybe that was the temperature when the universe was created. So right when the universe was created, I'll just say creation of the universe, which some people call the Big Bang. Now, whether it looked like a Big Bang or not, we're not for sure. But when the universe first existed, the energy of the universe was at its maximum temperature-wise. And so they think it was about 10 to the 27th power Kelvin. And then after that cooled down, energy dispersed, went throughout the universe, and it's cooled down ever since that first day. Some people think, though, it could have gotten hotter than that, and that the highest temperature possible in the universe is this, 1.42 times 10 to the 36th Kelvin. It's called the Planck temperature. And that's the highest temperature that makes sense. Above that temperature, things just break down and the equations don't work. And so while this is the highest temperature they think ever has existed in the universe, this is the highest temperature that ever could exist as far as they're concerned. Because above this temperature, our equations don't work anymore. Now, your book doesn't think there is a highest temperature, and it says that, but that doesn't really make any sense because temperature is related to matter and energy and matter are finite. And we only have a certain amount of matter and energy, and we can't create matter and energy. And so whatever was given to us in the first day of creation can't change from that first day. And so from what I think, there must be a highest temperature because how can you have infinite energy? We don't think that's possible. But the highest temperature is still up for debate. These are some ideas of what it could be. Okay, last thing today I want to go over is how a refrigerator works. I'm trying to draw this. So you have a compressor. Choose a different color for this. So a compressor is the noisy part on your fridge. It's the part that makes, you hear it when the fridge runs. So it's working to compress the air and make it smaller. So energy goes into the compressor to do that. So as it compresses the air, it's doing work on the air. It's making the volume of the air smaller, and it's doing work on the gas. So it's giving energy to the gas when it condenses it, or when it compresses it. Then the compressed gas goes into these coils, into a condenser. In the condenser, what happens is that the gas gives off energy to the surroundings. It gives off heat. So it goes from a gas to a liquid. That's what condensing means. Condensing means that you go from a gas to a liquid. So the gas turns into a liquid, And when it does that, energy is lost. Energy is given off to the surroundings. And that's why the back of the fridge feels hot to you. You're feeling the energy of the condenser working, where the heat in the gas leaves and it goes from a gas to a liquid. And then from there, it goes into an expander. So this high pressure liquid goes into a low pressure area where it expands. And as it expands, the gas itself is doing work. And we learned before that if the gas does work, it cools down. So as the gas expands, it's cooling down. And it cools down to about -27 degrees Fahrenheit. So as it expands, it gives off heat. It's losing energy, and it's cooling down to a very low temperature. And then at that point, it goes into an evaporator. So now it goes from liquid to gas. And as it does that, it has to take in heat. So if it goes from a gas to a liquid, then it has to give off heat. If it goes from a gas or a liquid to a gas, then does the reverse. So over here, as it goes from a gas to a liquid, heat goes into it. And that's why evaporation cools you down. Because as a liquid on your skin evaporates off your skin, it takes heat off your body. So evaporation involves heat being removed from a surface and going into the liquid to turn it into a gas. And this heat that leaves is from the refrigerator, the inside of the refrigerator. So this is how it cools down. Now the fridge itself is at 34 degrees Fahrenheit or so. It's usually what you have the fridge at. This gas, though, is about -27 degrees Fahrenheit. So even though the fridge is quite cool, it's a lot cooler in here. And so the fridge is hot compared to the gas in here. And that's why heat can leave and go into the evaporator, because the temperature difference. Even if two things are cold, if one thing is colder than the other thing, then heat will flow from that cold thing to a colder thing. And so that's how you can remove heat from a cold object, is you have a colder object outside of it. So the refrigerant fluid can get about 27 degrees below zero. And when it encounters a fridge, which is quite warm to it, it takes in energy from the fridge and cools down the fridge. And then the process just continues from there. It's just in a cycle. From the evaporator, it goes to the condenser, the gas is, or compressor, the gas is compressed again, and it continues the cycle. Let me show you a picture of a fridge, just to make it a little bit clearer. If I can find that for you. Okay, can you see the fridge picture now?
Yes.
Okay, so those are the parts I drew on the diagram. You can see down here the compressor at the bottom of the fridge. So that's where the cycle starts. The fluid is compressed. It goes up into here in the condenser. And so as it condenses, as the gas turns into liquid, it gives off heat in the back of the fridge. And that's what you feel as the warmth from the fridge. Then it goes into an expansion valve where the high pressure liquid right here moves into a gas form, and it cools down as it expands to about 27 degrees below zero. Then it goes into the fridge itself along the evaporator area. And so as this fluid evaporates, it takes in heat from the fridge. And so the fridge is about 34 degrees Fahrenheit. The evaporator is about 27 degrees below zero. And so heat flows from the fridge interior to the evaporator. As it moves along the fridge, it removes energy, cools down the fridge. Then it goes back down here to the compressor and continues the cycle. So those are the main parts of a fridge and how it works. Hopefully that wasn't too complicated. I know there's a lot I just threw at you there. But you don't need to know all the intricate details of the fridge, just the main idea about condensing and evaporating. The main thing to take away from this is, well, there's a few things. when you condense something, it moves heat from that fluid to the surroundings. So if I were to have steam on my hand, the steam causes a severe burn for a few reasons. So the steam can be quite hot. It can be well above 212 degrees Fahrenheit. That's one reason why steam can burn you. But besides that, steam also is going to condense. My hand is a lot cooler than the steam. My hand will cool down the steam to below the boiling point. I feel the heat of condensation. As the steam goes from gas to liquid, it will deposit energy onto my skin. And so I feel both the temperature of the steam and the heat of vaporization that will deposit on my skin. And that's why steam can cause such severe burns, because you have two things that are happening. Energy of temperature that can hurt my skin, and energy of condensation as the steam goes from gas to liquid. So that's the main thing to know, is that condensing results in heat being transferred to a surface. And then in the evaporator area right over here, evaporation cools down things. And so evaporation takes energy away from the surroundings. And the fridge is about 34 degrees Fahrenheit. This is about 27 degrees below 0 Fahrenheit. So heat will flow from the fridge to a cooler area. So those are the 3 points to know from this. You don't need to know all the parts of the fridge, the cycle of it. Just know those 3 things I just told you. And I can write those down too, if I can get the whiteboard back. Let me see really fast. Okay, do you all see the whiteboard now?
Yes.
Okay. So just to recap, you have the condenser, which heats up the surroundings as gas turns into liquid. The evaporator does just the opposite. The evaporator will cool as liquid turns into gas. So these are reversible things. I mean, condensing is going from a gas to a liquid. Evaporation is going from liquid to gas. So as you condense, heat is given off. So over here, the heat of vaporization is given off to the surroundings. When you evaporate, just the opposite happens. With evaporation, the heat of vaporization is given to the substance. Let me try to draw that for you. Okay, so if you have an object, so you have some water right here. Actually, sorry, we should have a gas. So as the gas goes to a liquid, the heat from the surroundings is given off. So heat leaves. And if it's on your skin, it will heat up your skin. Down here, liquid to gas, just the opposite happens. Heat goes in to the object, which will cool down the surroundings. Does that make sense? Okay, so that's it as far as notes go today. I'll give you a few homework questions to do, and we'll end here for today. It's questions 27, 30, and 31. I'll write those down too, but it's 27, 30.
Are those on, Miss Holly?
It's on page 331.
Okay, thank you.
And we're going to have a quiz over this tomorrow, just what we talked about today in class. The quiz will mostly be about homework questions, so I would just focus on those, 27, 30, and 31. That would be the main thing I'm going to quiz you on. I won't quiz you on like the refrigerator and how that works, but just know the homework questions. There'll be similar questions on the quiz.
Are we going to be doing the chapter review this week?
Yes, we'll start that on Wednesday. Yeah, that's a good question. So for this week, we have a test on Friday. Well, you can take the test anytime up until Monday, but I'll give you the test starting on Friday. And we'll do the chapter review Wednesday, Thursday, and Friday, and the test after that. Anytime over the weekend, up to Monday at midnight, you can take that test.
Okay, and then how are the study guides for the finals going to work? Like, are you going to send them out in pieces or just send the whole thing? And
I'm
we can
going
send them
to
in
either
DPG.
deliver it or Miss Klisky will deliver it, or I'll mail it to you all. So
Okay.
we'll get it in paper because it's just so much to print out. I don't want it to make you all print it out. I can give it to you through email too if you want to print them out yourself, but I don't want to make everybody print out a lot of pages. So I already copied them all, and they're already going to be either mailed out or delivered to each of your homes.
Okay, great. And then how do we get those checked by you, like, after we fill them out?
Yes, after you fill them out, you can email me for answers.
Okay, great.
And then they'll be for a grade too.